Okay, we're all set. Welcome everyone to this first workshop in CVII. This session is recorded, so we will be able to make it available to those who cannot join, to anyone from our Asian time zones who are staying up late. Thank you very much for joining us. But this will also be made available at a later time, at a more convenient time for Asian time zones. And I think we'll just get right into it. As usual, we have a number of different interesting things we wanted to talk about. So this workshop will have a couple of presentations and demonstrations. And it is a workshop, so those of you who are here live, I hope that you will participate lively and yeah, that's all I want to say as introduction. Here's the agenda for today. At first, I want to talk a little bit about the alignment track, a very important activity for meeting the goals as they are stated in CVII, which is to really achieve that industry-wide common data model and services model. So let's talk about a little bit where we are there and hopefully get all of your input on that. Then we will have a demonstration about parts of the technology stack. The term technology stack, as you may know, is how we define the activity of creating the common software, essentially, that can transfer and run the functionalities according to the data and services model. And I'm looking forward, as always, to hear from Bosch, especially considering there's a recent open source framework that is a very, very good starting point for the technology stack. After that, we will look more into the VSS Ontology project, led by Daniel and Christian. And that's very interesting to hear how the ontology approach can make the connections from the VSS model to perhaps other non-automotive domains and describe deeper relationships between data. There you will also see the connection, the first ideas around how it can connect to digital twin description language. All right, let's get right into it. I'm going to make a little introduction, and then if there are any questions, feel free to pop them into the chat, and if there's a bit of a break, you can just unmute and speak as well. We created this picture to give a little bit of an overview how we see the landscape currently. Not claiming that it is fully complete, of course, but it gives us a starting point to look at what organizations and projects might be in the area of thinking about data standards and services standards, and thinking about how we align all of these things into working systems in the end. That's really a key part of the CVII work. And we mentioned before, as you may have heard, that CVII, we sort of feel that before we put a name to this, all of these activities existed, but the communication wasn't really there to truly figure out how all of these things should fit together and to align, hopefully, on a single way of describing data and potentially also services. So that's the overview. As we can see, international organizations, some working with traditional standards work, some working uniquely with their members, and others working in a more sort of open licensed fashion. And we have here a complex landscape to navigate through. But looking at the details, I'm very hopeful because I don't think there's such a technical mismatch. And I think we are seeing a lot of movement towards alignment and perhaps agreeing on how we do describe data. I just want to go over a couple of areas here. AUTOSAR, and I'm happy to get your feedback on this, because this is, of course, just kind of a proposal for how things are. But the format seems to be well defined. In AUTOSAR, there's AUTOSAR XML and the ARACOM abstraction. I seem to see a consensus in the industry that AUTOSAR builds a technical platform, but is less focused on creating a list of standard data definitions. And basically the same is true for interface definitions. If nothing else, when we talk about all interfaces, it's of course a very large undertaking for any activity to work on standards there, and it has to be done very widely. And I think what our first goal there is to talk about how we describe those interfaces, and if those interfaces are described in a certain way, how do we make the technology that connects everything together? And so when I say to a small extent, you may know that AUTOSAR, does have standard services but they're mostly platform services. They are well defined within the platform how you use certain things, like and the obvious one being diagnostic, which has been available since AUTOSAR classic platform and so on. But in the wider sense, there isn't a large push to make the actual component interfaces standard across the industry. I think we've shown with previous work that it's feasible to do this kind of thing. Some of you may know about the Franke IDL to AUTOSAR conversion in both directions. We showed that running in the demonstration where there was the interface was only described once, but code was generated with AUTOSAR tooling and non-AUTOSAR tooling, you could say, and the communication between those systems working with only one description of the interface. So the feasibility of doing this with a combination of AUTOSAR and non-AUTOSAR systems, I think we've shown. The road ahead seems fairly clear. We will create translation tooling between VSS and VSE and AUTOSAR XML to test this out and uncover if there's any kind of semantic mismatches. And then we can take it from there. Obviously, we have more discussions between involved companies to establish some agreement on the usage of the common data model as a principle for both non-AUTOSAR and AUTOSAR systems. And also somewhat vague here, but I know there's some ideas within AUTOSAR to describe sort of the behavior of the whole system scope, and including the cloud side. And that type of activity, of course, we need to talk about so that we have a consistent view across the entire scope of automotive platforms. Sensoris, we've done a little bit more work, as I mentioned in the update, the project update. Here's a rough overview how I may see, or we may see, Sensoris today. Again, happy to get your input on anything that we missed. Sensoris defines data and messaging protocols. So we can see that the data focus is primarily focused on sort of the environment, which means measured things outside of the vehicle, and also related to map data and navigation type information, whatever you can sort of see as the outside environment. and perhaps a bit less focused on data that originates inside of the vehicle. And the VSS basically has the opposite split. But there's definite overlap here, since a vehicle measures things like outside temperature, and that becomes then a measured signal in the vehicle, and covered by VSS today. Sensoris has a significant focus on defining the message format. The messages are defined using protobuf, and you can see as you dive into this that there is more structure than simply the value itself. So I made up some examples here just to make this clear. A message could tell you something like this: there's a traffic sign warning about construction, and it's been noticed to be located here, and it's located above the second lane of the highway. And so I don't know if they have exactly that message, but that type of information shows us the relationship and location of things matters in addition to the information itself. Another thing might be that you measure a value and you state that measurement was taken on the left side of the vehicle. And in fact, that is stated with an exact position rather than just saying the left side. So that requires a more elaborate relationship description and therefore a kind of a level of complexity, which we also can see in the message format. So there's a need for that complexity, but I also see that it's something to be avoided when we don't need it, so to speak. Interesting feature of protobuf is, of course, that if you describe a complex message structure, you can sort of choose to use only part of that in a particular message. So from a technical perspective, that's a workable approach. I would say that VSS and VISS and related projects really emphasize the separation of the definition of data from the way it is exchanged. And it's possible that sensorists do this as well, but I'd like to do that we do more analysis together to figure out what are actual data items versus relational information. Let's see, we're a little short on time, so I'll speed up here, but these are things we can refer back to. The unification around sensorists, I think we can work on these types of actions. We need to talk about the importance and usage and understand where and how companies want to use it. Of course, looking at other similar activities, that's just a general point. Work on the overlap or duplication of all those signal definitions. In our view, most of us promote the kind of VSS-like standard catalog for data values that are of that nature that they can be described in VSS format. Of course, we're talking here about the models and rules alignment first, and I don't want to go into who maintains that catalog, because that could be multiple organizations. That could be something we split between us. And that's usually a sticking point for many. And I don't want us to get stuck on the kind of ownership of standards when we're looking towards a common standard. The important thing is the technical alignment first and making sure that that is feasible. Obviously, we need to maintain the understanding of what needs more elaborate messaging, as Sensoris has shown in certain areas. We need to consider, perhaps if we really drill down to the actual data of Sensoris, that the data types are of simple types, and in those cases, we should align around one way of describing those as we do in VSS. Essentially, last point here would be that protobuf usage is a common point. It's definitely something we could elevate in as we build the CVII technology stack together, and think we can find common ground there. So, to summarize, we have several CVII related activities fully based on VSS. CVII has so far proposed VSS as a starting point, and then getting all the input from other stakeholders in other parts of the industry. However we do it, we're dead focused on the goal of finding this alignment and making it work. VSS is deliberately simple, chosen data type, so there is a usage for that, and there's a strength in that. But sometimes we need to look at, not jump to a more complex model because it can do everything, but rather look at how we create that combination and that usage of these different tools. VSSO is there to connect and describe links and relationships, a very interesting development. And we should also mention that the VSC, the service catalog as it is described, actually is able to do arbitrarily complex data types. So it's a possibility that the combination of these could fill all the needs. What matters again is the technical agreement underlying model and format. And in the spirit of this goal to find the industry-wide data model, it's required to unify VSS and any other activities to a single consistent way of describing. And I'm describing a kind of plan B here because if there is an outlook where we find that there is actually a technical need to do things slightly differently in different places, then what we need to do is to describe an agreed upon a relationship between these different parts. So if the CVII goal ends up being the two agreed upon data models or something like that, that's perfectly fine. We can unify that to one concept, but we do need to describe how these are going to work together. We cannot leave it as we have done so far with diverse things that just develop on their own, and then there's a complex mess to figure out how to build a complete system. So that relationship between different parts sort of unifies things and brings them into a common answer in the end anyway, even if technically you might not call it one data model or another. Finally, of course, identify any and all related and similar projects if we're going to achieve this goal together. And I see my time is up and I've used up most of it. Thank you so much for your inputs on the chat window. We have of course, workshops later this week as well. So I hope you bring all these questions and we can take a little bit more time to discuss them in more detail. And if we have any time at the end of this session, we can also return to it. But just to make sure everyone has time to present, I will now turn things over to Bosch, and looking forward very much to your presentation.
Thank you very much, Gunnar. So, we were called to give a presentation about the vehicle edge. So Lars and me will present you this repository. We start with a first overview about the components. So I want to show you a deployment diagram and give some sort of hints about what has been changed in the last weeks, months, and what we are currently providing there, and give you also some feeling about the data flow from the sensors below up to that vehicle application. So, and after that, Lars Kiefer will give you an hands-on and a deep dive on several topics about that. So give me a second to share my screen. Hope you can see it now.
Yes.
So this is the repository of GENIVI Vehicle Edge. I want to use the recently curated deployment diagram to give you an overview for that thing. So what is in general the vehicle edge is maybe the first question on your head. So this is a software stack to provide at the end so-called vehicle applications. So vehicle applications are staying on a very abstract level above VSS, and also by VSS providing and integrates the vehicle below it. So this is also represented as a diagram here. So the top level is the most abstract level, and the lowest one is here this as called as vehicle core, which is providing the sensors, for example, and actuators inside a vehicle. So So we choose the deployment diagram as a first documentation because it's the reason or the idea behind the vehicle edge is simply to provide the deployment of existing components we have. So one base thing is the IoT event analytics platform. We are using it for the vehicle applications as well as for the platform directly and some platform services. So this is the upper part here. And below that, we provide additional stuff to integrate this IoT event analytics platform inside a vehicle. So one important thing is for the vehicle applications, we have 3 abstraction layers, which is where we think is very important inside a vehicle or for a vehicle application. So one is the data abstraction, of course. So as I said, we're using VSS as abstraction level for the data and integration inside into a vehicle. The other abstraction layer is a communication channel. So as you can see here, we are staying, this is the default deployment, but we have many options to change something. And one of that is this MQT broker we are currently using, this Mosquito MQT broker. Recently, we have provided an abstraction layer for that, so you can also now exchange this MQT broker by something else, like SumIP, for example. So it's only have to provide a pub/sub interface and some specific requirements from our side. But at the end, we are very flexible to deploy also our vehicle applications on a different communication stack below of that. So we want to be very flexible on that side as well. And we have also, of course, we have seen a different use case for vehicle applications. So one of them are for example, deeply embedded use cases, but we also see use cases like analytics or also very fancy stuff for third-party applications. And therefore, we have this also made an abstraction level above the communication and on the language level. So that means at the end, this has to be a client which has access to the communication stack and has to follow our protocol using JSON as an exchange format. So currently providing 3 SDKs for that. Node.js is default one, Python for example, analytic use cases, and C++ for more deeply embedded with less footprint and high performance requirements. Yes. Below, is there some question?
Jochen, I'm just wondering if you could. It's not really filling the whole screen. Is that?
It's not filling. Oh, sorry. It's sharing. What can you see now? Is this only?
Yeah, it's on the left side of the. Yeah. Okay. Now it's getting bigger. Yeah.
Can you see the whole thing now? Sure.
Yeah, it's not really full screen, but it is. You have made
maybe
it
like
bigger.
that.
That's better. Yeah.
Okay. Sorry, I was thinking about this, so it was completely. Yeah. Okay. Perfect. Thank you for the hint. So okay. So we was talking about the vehicle applications here on top, then about the platform, the abstraction levels of that, and beside of this platform, we have also so-called platform services, which are the integration layer from VSS to the IoT event analytics platform to this platform component and the vehicle applications on top. This is a very lightweight component. It's simply only some control channel to communicate to the lower levels to control which data will be filtered or transferred to the system. And this is then it's only the integration into the platform. It doesn't do anything about the mappings or such things. It's only a representation change. Below that, we have the vehicle integration. This should be seen as a placeholder. So it's not a final solution for end customers. It's more or less to develop and also bring up the whole stack to test it out, to get a feeling how this should look like, or could look like. These components are used to have one purpose is to connect to the canvas and map CAN signals to the VSS afterwards, which is done by the whole interface adapter here on the right-hand side, which is simply then map the values to the VSS data points to get the value on the upper layers. So to get through and summarize everything, so what happens is a sensor, an actuator publishes a signal on the CAN interface. This whole interface adapter takes it, puts also on the pub/sub channel here, and the whole interface adapter can subscribe it, can map it to the VSS data, make the abstraction to VSS, and this platform service simply integrates and controls this integration and publishes it and provides it at the end to the vehicle application on top. So this is the whole chain, how the system flows through it. Beside that, we maybe one thing to mention here, IoT Analytics has been chosen also because it has a very high feature set on subscription level. So we provide so-called rules on rule sets to subscribe to vehicle data, also VSS data points in this case. That means you can have very complex rules which are check if values of the data tree is a certain value, or it's above a certain value, or it has been changed. Or we have also some Nelson rules and time constraints which you can use to integrate your business code as a vehicle application to the system. So it's a very rich feature set to interact with the VSS data points. Okay, that's more or less all from my side. So Lars, could you proceed with your hands-on?
Sure. Thank you. Thank you, Jochen, for this introduction. Now I share my screen. Okay, can you give me a hint if you can see my screen?
Yes.
Okay.
It's good.
Okay, so the last time we had a demo, we showed how to create a vehicle application from scratch. To save some time today, I already just clicked on a button once to create a basic project here. We are supplying a Visual Studio Code extension, which helps out a lot of creating boilerplate code and some default configuration. It's basically choosing an empty folder and you're good to go. I prepared that in advance because dependencies have to be installed and fetched, and therefore we can just save a bit of time here. What is actually done, it creates a default configuration of the whole platform here. And just, but to lift off at the VSS point where's our first point of abstraction, there's currently no VSS binding in here. So if we are looking in our types configuration, we do not see anything about VSS, so there are actually no VSS data points available. I would like to start here because now there is a very easy way to get all the VSS data points into that configuration file here, that we are able to use it in the platform. To do so, we're using the extension here, and we are creating this configuration from scratch. That means when I'm clicking on here, we would like to add this vehicle signal specification to an existing file, to our types configuration. We just click here on yes, so I have to choose which one I would actually like. I click this types.json here. This is the document we looked a few seconds ago. Just click on open here, and then it tells me, okay, please select an output folder. Everything is okay. I will talk about this segment number in a minute when it installs everything. I just hit enter, and then I'm saying, no, I do not have a vehicle signal specification file already. This means I do not have this VSS JSON document here. I say no, and now it clones everything from the vehicle signal specification repository and builds everything for me from scratch. Since this takes half a minute or so, let me tell you something about this segment we saw. This is basically, we are organizing our data in a hierarchical manner, and the topmost point is a so-called segment. This is represented by an E-class, and an E-class is kind of an industry standard for IoT devices, and this is the number referring to a car. So now it's cloning all the submodules, and now it's creating the vehicle signal specification from source. So it has to install, we are using the provided VSS tools in that repository. That means all the Python dependencies are currently installed for me. And then the specification is created, the VSS JSON, and then we are adding it right into our types configuration file. After that, I will just give you some hints what we will do afterwards. Then we will get into the code, and then we will show the new things which are actually possible currently. Okay, so done. Let's look in here. So here we are seeing the new segment, and here are all VSS data points together with all the metadata which was provided. So good. So now this is we took this as a starting point, and this second folder here contains exactly the same thing. And now let's go into it. Let's go into the code because I mean it's a hands-on. Therefore, let's get into it. Jochen talked about vehicle applications. Since we are here in the domain of this IoT event analytics platform, it's called Talent, but these are just synonyms: vehicle application or Talent. as Jochen pointed out, a talent has a rule set. Currently, we have the default rule here. So we have a data type, which is called any type and any feature. And we would like to be informed once this data point is set. And then, since we have an event-driven architecture, we have an on-event function. And this is triggered as soon as this rule set actually applies. Just to make it more obvious, let's just start it. We are currently looking at a JavaScript talent. Jochen pointed out that we have more SDKs in place, but we currently only integrated JavaScript into this Visual Studio Code extension. Okay, now there's one more thing to go. We have to get an event into the pipeline. Basically, this event could be sent from the CAN bus down below. It doesn't matter where it actually comes from because this is handled via this integration layer. But for the ease of use, we use our integrated MQTT publisher. This is also shipped together with our extension. And here we can just see it is bound to the platform and it just receives all the available types. See also here the whole vehicle. So the whole VSS stack is presented here. But since we're just listening for that any type, any feature, we just can pick a value here and send the event right into the platform. As soon as I'm sending it into the platform, we'll immediately see here number 5 is transferred into the platform. So this is basically how it works. But now we'll get to the new stuff. This is what we showed last time, and there we stopped. But we have more things to show actually. So a talent, so a vehicle application can not only react on some events, it can also act as a function provider or as a service. To do so, we unified our APIs to make this possible. So instead of requiring a talent, we're requiring a function talent. I mean, this is basically it. And since we unified our APIs, this is it. Now we can provide functions. To provide a function, I mean, let's write a function. Let's call that linear, and we provide an x and an m and a c. I mean, this is a linear equation. And then we are returning x times or m times x plus c. So this is, I mean, this is basic math. And to make it available, we have this function here, register function. We have to give the function a name. We call it linear so that I can call it. And we're specifying the callback. The callback is the function I implemented. So that's basically it for providing functions. But how can we call these functions? To be able to call functions, since we are completely event-driven, also function requests and function responses are events within our pipeline. And since we are rule-based, we have to provide which functions we would actually like to call. So therefore, we have this function callees, which returns an array of functions we would like to use in our vehicle application. In this case, it's quite easy and straightforward. We would like to call ourselves. So this is also possible. We can call our own functions. And to do so, I handle the ID because every function is within its own namespace. So this refers to that string here above. And we call the function linear. Okay, now we made clear we would like to use that function. And now we can simply use the onEvent function to say, to call that function. Let's do that here. Since function calls are always asynchronous, we can use the await statement here. We can just say this call. Okay, we'd like to call it. Since we are the actual provider of the function, we're passing in this ID. Here's the function name. Cool. Now we have to provide all the arguments. It's x, m, and c. Therefore, we say, okay, as x, we take our input from the event. In our case, this any type, any feature. We take that one here. For m, it's 4, and for c, it's 5. I mean, these values can also come from somewhere else. Yeah, but for the ease of use here, we can just do it like that. Okay, let's see something else. Yeah, a subject. Because every event which occurs in the pipeline belongs to somebody, and therefore we have to pass the subject. And the return topic is always a good thing. If we want to say something, we always respond to that topic. Okay, now we are good to go. And let's see how this works. We just have to restart it. Okay, now we have to wait sometime because currently the platform is now discovering the some unique talent ID, and now it also discovered all the new fields. Since we're providing a new rule set, as you can see here, we are relying now also on outputs and inputs of the function. We can now just send MQTT messages right into it and see if this function is actually called. Go to the command palette, click publish. Wait a second, okay. Any type, any feature, pick a random value, it's 14. Let's see. Okay. Oh, that's the demo god again. Who's among us? Let's see. Ah, no, okay. Whatever. So it's 61. So it actually executed our function and printed the result right onto the console. For sure, it is also possible to call functions of other function providers. I just have to note them down, which I would like to call, and then I'm good to go. But it doesn't matter if I'm implementing a vehicle application, so-called talent, or a function talent. I can just make it, I can just use it the same way based on our unified approach here. Why would I use that? Functions can, for example, collect data in the background from the vehicle and then do some calculations based on that data once the function is called. Allow me one or two more words about this platform as abstraction Jochen told you before. Let's look into the configuration of this platform, because here it gets quite obvious. So here we have our protocol gateway abstraction layer, and we are providing a number of adapters. So it can be an arbitrary amount of adapters, and they get dynamically loaded as they are needed. So for example, a some IP adapter can easily be just added via a configuration parameter, and you do not have to recompile some code or something like that. It can just be placed next to the platform and is ready to use. We also had made progress in, let's say, quality assurance. So we integrated unit testing for all our SDKs, and we integrated integration testing for all the whole platform, and for each SDK. So all the SDKs are automatically tested using GitHub Actions. We also made progress in the documentation. As Jochen pointed out, on the architectural level, we increased the amount of documentation, but we also started to document our code directly and generate documentation via JSDoc. So the documentation is always up to date, and it is directly built when you're cloning the repository to your local PC. Okay, 1 minute overdue, but I think I'm still in time. So, are there any questions from your side? Just go ahead and shout out. Questions?
There have been a few questions in the chat, but feel free to just unmute and ask.
A quick question. This is
Yes.
Rajiv. I put it in the chat, but I'll just ask anyway since you're asking questions. So you showed a generic architecture for a protocol gateway. So can you? I mean, you mentioned several different technologies, MQTT, some IP. Can you also add others like a DDS gateway?
Potentially, yes.
Okay. So
because we have quite a the interface which needs to be implemented. It's quite an easy interface. This just contains the 4 methods, and if you provide these commonly known pub/sub methods, you're good to go. And because the platform doesn't care about this underlying protocol, it's used for the transport, and the platform doesn't see it. It just sees this gateway interface and nothing more. So it's possible also to have DDS as a protocol. Sure.
All right, thanks.
Yeah, a quick comment there as Gunnar speaking. I'm very eager to speak to you more about that, Rajiv. as we define what we call the technology stack, it's about talking to companies about what the most important technologies are to create a common system, right? We don't need a very fragmented situation in the industry with respect to these basic communication technologies. We want to spend our time on innovation and actual end user functions and so on. And so talking about how DDS fits in and how we may enable it, I think is a very interesting question. As I mentioned some IP before as one of the AUTOSAR technologies, but of course DDS is also there, and perhaps on non-AUTOSAR platforms it's a popular choice as well. And so if the industry wants to make that a part of the so-called technology stack here, then we should talk about how we can achieve that and create all of these connections, whatever it may be, connections to libraries, implementations, or maybe it's done through code generation or something else. And that's valid both for data and, of course, for remote procedure calls as we define the services standards. Okay. There was one question around the use of Docker, which Jochen answered in the chat. I don't know if you want to comment on that, but it's of course a very useful way to develop,
yes, sure.
regardless of how you deploy it in the end, right?
So we chose containerized approach due to security and isolation reasons, because when you're running containers, you get quite a good amount of isolation and security for free. And since this platform actually aims in the end to run the third-party vehicle apps as well, we have to be very sure. We have to make very sure that they stay within their bounds and that they cannot escape these bounds. And this was actually our starting point, where we said, okay, use containers, but the container runtime. So at least in my opinion, we are not fixed, or we are not stuck on Docker. Docker is just used because it runs well locally on my machine. On our end devices, we are using containerd. So basically Docker also uses containerd, but we're using some stuff built around containerd. But you can also think of using Podman or something else, because we're relying on OCI OCI images. I mean, this is a common image format. So actually any containerization runtime stack will fulfill the needs. So, I mean, when you're looking at it from a performance point of view, why don't we run on bare metal? This is the reason, because we want to move away from the pure solution driven business with that platform to a more to a product platform where products can run, and therefore we need that kind of abstraction. We cannot build this platform for each and every end device separately. I mean, this comes at a cost, yes. So the abstraction and generalization always comes at a cost. But I think when we keep the size low and the footprint low, we can achieve this goal quite good.
But in the case of containers, there's no practical difference in performance. Not on Linux.
No. So as far as I know, I mean, for sure, it produces a bit of overhead, because you have this overlay networking, you have the overlay file system, and so on. So you have a few things which come with these containerization stuff. But I mean,
it's rarely a practical problem in my view. I'm sure if you're looking for maximum network throughput, something like that, it may affect it. But the actual execution of algorithms, of course, is the same, and any kernel calls are exactly the same.
Yes.
It's not like virtualization, I mean.
Yes, right. Yeah, sure.
And I think we will see a unification of a lot of the technologies here, generally speaking. But we're starting from a point of looking at what does the reality look like. So if we look in vehicle, for example, there are multiple platforms and operating systems being used, and so there's still a diversity there, and there we have to talk about what are the common standards across communicating between these systems. And over time, the actual core of the executing platform will also be more and more similar over time. But we're talking about things initially, standards that have to do with how systems communicate with each other, even if they run on different platforms. You may see this in, for example, when we talk about Android as an outlier, but it's interesting, therefore, as the Android SIG is doing, to talk about how that fits into a VSS-based reality, because then it becomes part of a larger whole and a larger vision for how to build the complete system, as I like to call it. I like to call the complete system as not as individual parts, but the entire thing that includes vehicles and the cloud and perhaps third-party applications and so on, because we're gonna see a consistent view of that whole thing as we go into the future.
So you talked about specifically a third party, right? I just have a question here. Does your standard also looks at some of the platform challenges of running these containers in the vehicle, right? Especially when it talks specifically about ECUs or where you deploy. There is a lot of aspects of power management, network management, and things that kind of goes into the platform, right? How do you see those containers getting integrated, or those applications getting integrated into that in a seamless way? I keep making sure that the containers are launched in a time to a vehicle mode or state or whatnot, right? So
yeah,
does your standard?
Do you want to take that, Jochen? Or do you want me to answer more generally?
Sorry, if I got it completely, so it was about the container management, how to get it running and such things, and to control it on the runtime.
Yeah, in vehicle and to concretely run it on actual vehicle platforms, as I understood it.
Yeah, also we're currently investigating to integrate existing IoT hubs and agent systems for that we, of course, think about what information is needed for the manifest file to deploy that, also regarding access control and security stuff. So this is currently under investigation, so we have no final solution for that. I think will have one in maybe several months, but I think it's ongoing and very important topic. Yeah. I hope it's also I have no concrete answer for that currently. So currently this is not done in a more manual way, but it will be changed, of course, to an automatic one, using an automatic approach for that and a well-defined approach for that thing. It's, of course, driving a lot of topics for us, especially also security and flexibility and also performance reasons again, how to bring in the requirements, how can the applications be configured, and what are the platform and applications from third-party developers. So it's a lot of topics, and we're starting with the management itself, to deploy these containers, to install them via an workflow. And next thing is then, of course, to establish then the configurations for that things and ingest the requirements and check and compatibility and such stuff.
Yeah. Oh, great. And I would refer back to my previous answer that we start with, generally portable software, general frameworks that can be applied across the entire system, and then over time you have to look at how to deploy that on specific platforms, of course. I think it's time to switch topic again.
Gunnar?
Yep.
Yeah, Philip speaking. There was a nice comment made by Jeff about the use of the AutoSAR signal to service interface specification. Okay.
Yeah, it's worth looking into. That's part of the translation or alignment.
Yeah, and Jeff, it's a topic we bumped into a couple of times over the last 2 years, and also when I was managing the adaptive AUTOSAR demonstrator integration team. So I like it very much, and we will put a note on it and put it on our backlog, Jeff.
Yep, thank you. It's good to review the chat a little bit for the recording. I think we covered all the questions, and let's move on to the next topic. And once again, I want to refer to the upcoming workshops we have, especially on Friday. We have time to dive into all of these questions deeper, and to pick up in any of these things we have discussed over the week and go a little bit deeper on the Q&A and discussions. Now it's time for Daniel and Christian to take over. Are you ready to share?
Yes, I'm ready.
Great.
So I hope you see the presentation.
Yes, we do.
Okay, perfect. So first of all, thanks for having me. I'm Daniel, working in the BMW Technology Office Israel. And we split the presentation in two parts. So I will give an overview of VSSO, what it is, why we are doing it, and then hand over to Christian from Microsoft, because we were in the WCC discussions in the last week, so almost 2 months. We were as well thinking like how VSSO can be used for DTDL, and how an alignment can be done here, like based on the data model we are defining here. But let's jump into it, why we are doing it. So basically up to now, and this is the motivation for the whole CVII, so I don't have to talk much about it. Like previously, it was really easy to integrate different services, like for the customer needs. You know? Like it was basically end to end, done with the normal normal development of a vehicle component. But what has changed is that everything gets more interconnected, and with the interconnection, it's as well important that there's a common understanding to basically leverage from the knowledge other domains have for their own. So we are talking here about the vehicle domains, and where we started. The project was started before I got involved in 2016. Is like VSS, and it basically answers the question like how do we define and describe vehicle-related data? You know, like in simple terms, like with a really easy accessible language based on YAML, and with a really good understanding of the data points we are having. So, but then the next question is like how do we make this vehicle-related data understood by different domains? And then how to leverage that data, no? How to gain more insights and not new knowledge based on our data, and how do we interact at the end with the other domains? And like let's go through the solution stacks here we are proposing, and see how it can be used. So let's start with the first one. VSS, it was so much mentioned today. You saw it in the presentation before. Okay, we have a YAML-based description of a tree-like structure, which basically at the end resembles like the physical structure of the vehicle. And in the leaves, you see basically the data nodes as you see like with in the example with speed. But this is defined in YAML. Of course, as I said, it's like really easy to understand. But what it lacks is like how to really refer like to unique identifier you have, so that you can basically have relations between the different domains. No? Like this vehicle has been produced in a specific plant. This user is driving this vehicle and has several other vehicles. Now, if we want to have those relationships, we need more. We need more expressive semantics to basically define that. Of course, we can do it on the YAML base, but there are already standards for doing it. No? And that was the point when we were thinking of VSSO, which is already as well 2 or 3 years back. So that leads to the questions like how do we get the relationships to it, and like how do we make understood like our domain understood for others domain who want to interact with us. So there's VSSO. It's like a really brief history of VSSO. It started basically from the first version of VSS, where the structure was quite a bit different. We had like you see it here on the side. We had like basically subtrees for attributes and signals. We didn't have like the vehicle as a root tree, and but it was like what we saw then when Benjamin Klotz started with the development of the vehicle signal ontology. What we saw, it was one of the few really open standards, and as well which don't include like basically any protocol description. No, it really just came down to the data definition, which impressed us, and where we didn't see so much else on the market. So Benjamin used that and started with the first version of the ontology, VSSO, and basically we saw that some design decisions made it hard to basically make an automation towards the ontology. That it was hard to grasp the basic concept and basically automatically generate the ontology. What we don't want to do is we don't want that VSSO goes into a different direction from VSS. No, we want to keep it really closely aligned, and we will show later how we propose to do that. But then we thought, okay, like what can we change so that it makes it easier and that the concepts get more out, like that you don't have so much replication in the tree, that you can really express instances and so on. Those were basically based on the work we have done, basically proposals which went then to the version 2.0 of VSS, which was released like beginning of the year. And so in parallel, VSSO was now submitted as a member submission from the Eurocom, like end of 2020. And basically in the WSVC Automotive Business Group, we started to work on it. And like in the meanwhile, we made a proposal from BMW side, how we can ease the process coming from VSS to VSSO so that they can be close together. So like what we thought how to achieve that is that we first start with the core ontology. You know, like basically the core ontology should express like the basic concepts you have in VSS. We will see later as well, like an example, but this is basically something like branch, attribute, sensors, and like the basic concepts we have. Then we want to take like the concepts we define in VSS and basically use it together or like use it on top of the core ontology, which is defined here, and basically generate the concepts directly out of the VSS tree and automate that for the like based on the core ontology. And last but not least, we want to leverage as well other ontologies. For example, we don't want to reinvent the wheel. For example, we see later in analysis and so on, we want to use ontologies which are already there and where VSSO can be used as a domain ontology for those others like SSN SOSA or Web of Things or those ontology standards you can take. So once we have basically the idea like VSSO as an idea how to describe it, like then it's a question, and this is really important for the design, the concrete design of the ontology. We have to answer the question like how do we generate new insights and how do we interact with other domains and how can we use the ontology. So that is like before we started really like writing down the concepts, we defined a couple of use cases. We thought, okay, this is what we want to solve with the ontology. So we have basically on the one hand, we have analytics use cases. Like one is like, give me like in a graph, give me the current vehicle data, which is there. Basically something like a digital twin, or like we call it, and we showed it last time, like a vehicle shadow. It gives you the last state of the vehicles. And with that one, you can identify like the current values of a specific vehicle on the one hand, or you can say, okay, which static or dynamic attributes define a class of vehicles. Now you can say, give me all BMWs or give me all Audis or something like this. Now, like this basically, or like a specific model. So this is one kind of analytics we want to solve, that is like on current vehicle data. The second one is like we see like analysis on the dynamic vehicle data over time. No, we want to see how, like between two timestamps, we want to know how the values have been changed, and like we want to see observations. And there, VSSO can serve, and that was already in the first version like this, as a domain ontology for SS and SOSA. And last but not least, we want to interact with it. No, and there's a Web of Things. For those who are not familiar with it, I recommend to look into it. It's basically like you want to know how to like how to interact with the vehicle and how to get the values and get triggered by events. There are descriptions where VSSO again serves as a domain ontology for the Web of Things ontology. So what are the core concepts we are thinking about? Like I said, the root node in VSS is a vehicle, so we started from a vehicle. We then thought, okay, like what do we have? We have static vehicle properties and we have dynamic vehicle properties. So those dynamic vehicle properties can be written or read. So either observable or actionable vehicle properties. So those are the two options. Then we want to like say, okay, like this dynamic vehicle property holds a specific state and has a specific instance. For example, the door, like in the front or like in front left or something like this. This we want to express as well. And last but not least, it belongs always to a vehicle component. And this is basically the core ontology we proposed at the first time, and I say later as well, we are discussing it right now. And there are design decisions I show later where we are discussing, which are basically now under discussion, and where we have tickets and where we try to get maybe to a better solution there. That was the initial proposal, and I invite everybody to give the comments and the insights there. But based on this core ontology, we said, okay, like from there we use the VSS concept and generate them on top of as subclasses or instances of the core ontology. So we have subproperties from a static vehicle property, for example, and here we used individual. But right now, as said, the discussion is ongoing. So there are 3 areas we are like heavily discussing how we might improve it. For example, one is like to have the static vehicle property as a class and not as a data type property anymore. Here the same for instances, and the question is if we should use, instead of individuals, here subclasses. So we are discussing it right now. There are proposals. There is a tooling is available in a repository. When I share the slides later, I will add the links. And this is basically the discussion we have, and I invite everybody to join there. So, but what we agreed on is that VSSO shall be like fully OWL compliant. And everything which is not should be treated as a bug. This proposal had been like in the rounds like recognized as a starting point for further discussions. We want to leverage from VSS what it defines, but what it doesn't define we cannot make up. So there's a question here about individuals or subclasses. And we want to use VSSO basically as a domain ontology for other standards, and we don't want to reinvent the wheel. So I will share the slides later. That was my part, and I would like to hand over to Christian now and show like how that can be used for DTDL, for the DTDL description, and give a bit more insight on that.
Thank you. We have 13 minutes left of the session, Christian.
All right, thank you so much. Let me share my slides. Oops, sorry. Can you see my screen?
Yes.
Perfect. Great.
It's not quite full screen though.
But you can see my slide.
Yes, we do.
Great. All right. So yes, hello, and my name is Christian Sherman. I'm a program manager in the Azure IoT organization, working on Azure Digital Twins. And thank you very much for giving us an opportunity to talk here today. I'd like to just give a little bit of background on our approach to digital twins, and then dive a little bit deeper into what we've been doing with VSS in conjunction with Daniel. So digital twins really are a design pattern for operational solutions that has really become increasingly popular over the last years, even though not necessarily everybody means the same thing with the term. But broadly, the idea of a digital twin is to have a full digital representation of as much as possible, ideally everything that matters to a business, and then have this digital representation brought to life with data from IoT and other data sources, so that we have a real-time state representation of that real-world environment that we then can derive insight from and that we can act to. And we're seeing interest in that digital twin design pattern across pretty much all business domains, where twins may represent anything from facility, things like smart buildings, manufacturing lines, or maybe an extension, smart cities, to products like twins of manufacturers' goods, for example, a piece of machinery or a vehicle, but also consumer goods, and even business processes. And we got very, very interested in VSS because we have several use cases at Microsoft and at customers where the representation of the state of vehicles actually really matters to customers. And really, Azure Digital Twins is a software platform that is designed to make it easier for developers to create a solution that is based on that digital twin design pattern. So in a nutshell, Azure Digital Twins is a modeling environment that lets you create your own domain-specific vocabulary and then use this vocabulary to represent whatever it is that matters to your business. And the way how digital twins represents an environment is as a topology graph with rich semantic relationships. And in addition to that data model, there's a runtime engine that you can feed with data to update the state of the graph with real-time data, and an event-based processing platform that lets you attach your own business logic to the data that is flowing through the graph, right? So that you basically get the combination of the graph representation that is queryable and that lets you, like look through all the data that is in your graph, but you can also attach business logic. Oh, sorry, I'm getting asked if I could make this bigger. Let me try that. I'm not using WebEx very much, so let me see if that works. Is that any better? Now, let me just go to full screen.
Yes, it is better. Yeah, full screen much better.
Okay, sorry for that. So let's use that. Where was I? Yes, right. So you have the graph representation that gives you, like a data model and the ability to query that, but it is also attached to an event-based processing engine so that you can, like tie business logic to that and actually do data propagation through the graph, and that you can do processing. And all that is combined with integration points that handle, like input of data from, like a variety of data sources, as well as output of that data to downstream services, in many cases, after, like the hot path or warm path operational decisions, people want to put the data in a data lake for analytics or send it to services such as Azure Synapse. We also have are working on a tight integration with Azure Data Explorer for time series data, in both operational and analytical scenarios. There are lots of integration points to connect the digital twin to the rest of your solution. So let's look a little bit more at the modeling aspects of digital twins. Oops, for some reason. Here. So in digital twins, basically, we're modeling a number of things. So we can model physical devices or sensors that get deployed in physical environments. We're interested in physical entities, buildings, streetlights, cars, storage tanks, and so on. logical entity, things like time zones or manufacturers, maintenance crews, and so on, and as much of the semantics of the real-world environment that we can capture. So one thing, for example, is we don't just want to say that data is in doubles and integers and booleans or whatever data type is, but you want to really say, what is the meaning of that data? So for example, you want to say, hey, this is a temperature that is measured in degrees Celsius, and there are many other aspects of that. In addition to individual entities, as the above, we're also very much interested of systems of digital twins, where many of these twins are combined into complex entities, basically a graph of entities that represents a larger a system or a larger business environment. And increasingly, there's also interest to have systems of digital twins, because you really want to bring together in many scenarios under one single pane of glass various subsystem digital twins that are potentially created by different companies and by different and are owned by different entities, so that you have complete different governance of digital twins that are federated into a complete system. So at the root of our modeling system is a language called DTDL, for Digital Twins Definition Language. It's an open source specification that is based on JSON LD. So under the hood, it's all RDF, triples, and shackle constraints that define a meta model that looks very much at the surface like an object-oriented programming model, so can be used without any in-depth knowledge of RDF concepts or shackle concepts or anything of that. And really, customers use DTDL to create a domain-specific vocabulary describing the entities and concepts that are important for the business, and perhaps even more important, describe how all these entities relate to each other and connect to each other. So the way how DTDL describes things is by properties, telemetry, commands, components, and relationships. Properties, really, as you would expect, represent, like the durable state of something. Telemetry is streams of measurements. Commands is effectively the equivalent of methods on an object-oriented model. And relationships basically say how things are related to each other. I always like to think of the relationships as the verbs between the nouns. If the entities are nouns, then the relationships are verbs connecting them. Like, for example, building contains a floor, or HVAC system cools a neighborhood, or things like that. We also use DTDL to describe IoT devices, so we have a plug-and-play model that puts all that together. And once you have your domain vocabulary, you can use that to build a model of your environment by creating instances of these specific entity types that you have and wiring these together in a network of things. So for example, if you, for a car, would have, like all the pieces of a car, the wheels, the axles, the motor, the chassis, the seats, right? A car could be modeled by connecting these things into a graph similar to what Daniel described before. So I'm going to skip that and jump to this. So our interest in the vehicle signal spec comes from that, as I said earlier, we have a number of use cases where we are interested in digital twins of vehicles. And so we were starting to look at how we could translate the vehicle signal spec into DTDL so that we could easily build a digital twin around vehicles. And so we tried two things. So first we used, like the existing VSS spec, the YAML-based stuff. And so as a first attempt, we used the unfolded VSS-generated JSON files, which are really easy to convert because it's just JSON. The problem with that is that you don't really create, like satisfactory twin models from that. And the main reason for that is the instancing scheme that is used in these YAML fields. Files that kind of like mixes, like the type definitions of what entities you have and an instance graph, so that you don't really get a very clean model that is nice in a graph database environment to use. I looked at, conversion from the your YAML files instead, which is a little bit more complex, but can create a cleaner model. But then we stumbled over the VSSO effort and we said, okay, let's try that instead. And it turns out it is actually fairly straightforward to convert, like VSSO models into a DTDL just using an existing open source OWL to DTDL converter that exists. And so we've done an attempt with that. And so this looks like a very, very promising path as VSSO matures to basically create a version in DTDL of the VSSO spec or the VSSO ontology so that we can use it in the context of a digital twin system. Just for reference, we've done that with other OWL-based specs as well. So for example, one of the current open source specs is for real estate model that is based on Real Estate Core, which is an open source OWL spec for real estate. And we converted that. The DTDL version from that is completely based on this OWL version with automatic conversion. So to show an example, the tool that you see here is called Adt Explorer. It's basically a visual exploration tool that lets you look at models and twin graphs in an Azure Digital Twins instance. So what you see here is a conversion of the VSSO model into DTDL, and you see these three blocks here of things that got created. The elements up here at the top basically represent the hierarchy. You have the branch here in the middle. All the green lines are inheritance, so all the things that are grouped around here are things that inherit from branch. And I'll show a clearer example in a second. I know this is a lot of stuff overlaid here. And then these things are assigned to signals and actuators that are these other two blobs here at the left and right. And as you can see currently in the VSO model, not all of these possible defined signals are actually wired up to any entities, just a subset of them are. But basically all these relationships come right through and can be used. So to look at that a little bit more in a hierarchical structure, so this is the branch structure that is coming through, into DTDL. So here we have a vehicle and a cabin. Cabin is part of a vehicle, and there are all these part-of relationships from the OWL that say, for example, HVAC is part of a cabin, sunroof is part of a cabin, lights is part of a cabin. And here, for example, we have the rear view mirror that is part of the cabin, and that has a signal which is the dimming level of the rear view mirror. And so here are another few. For example, the head restraint has a height, and the side bolster has an inflation. And here at the right, the cabin here is currently selected in the tool, and here you see actually how the DTDL description of the cabin looks like in this particular example. And here, this is now an instance graph snippet. So what you've seen here before, this is the model. So this is basically the description of all the entities and how they are related to each other. And this is a small snippet of a few instances of twins that are connected to make a graph. So in this particular case, I have the vehicle, a body, two mirrors, the mirror heater, and the status of the mirror heater. So what you can see here is that the light blue lines here represent the relationships that show how the things are assembled. So the mirror heater is part of the mirror is part of the body, and the body is part of the vehicle. And the pinkish connections show the signal relationship. So the mirror heater has a signal, which is the mirror heater status in this case, right? And this is obviously just a small snippet using just a few of the entities, but you could extend that to any complexity you like. And obviously, you would now have a subgraph of twins that represents a single vehicle. But of course, in a digital twins instance, you can hold as many of these vehicle twins as you like, which then in turn can make up a fleet of vehicles or a set of vehicles that you are tracking throughout the digital twin system, and where you would constantly feed it with sensor data from the actual deployed vehicles into the twin. And yeah, that is pretty much the set of things that I wanted to talk about. So we're currently working with Daniel to make progress on that and make this into a more complete and robust thing. So there's still a few things to work out. As I said, this was a first experiment and exploration to see how the VSSO spec can map into the use in a in our solution in our digital twins developer platform. And yeah, so much for that.
Thank you very much, Christian. We have reached our end time today. So we will wrap up this workshop. Once
One
again,
question here.
very quickly.
Yeah, so when we are doing this digital twin representation, right, we are basically monitoring the signals from each of these IoT devices, right? But where do we put the logic in that? Okay, for example, in this diagram, right? So how do you put the business logic in that? If R mirror and L mirror are throwing some signal and we want to show some telltale or some errors, how do we, where do we, like, what is the value of these relationships or hierarchy? How do we derive value out of these?
Great question. So there are basically in digital twins 3 ways of working with these. One way is you have a rich query system that lets you actually run queries about the system, where you can do topological queries that do graph traversal through the graph, right? Where you can search for things by state, by relationships, by traversals, and so on and so forth, which is often very, very powerful to extract insight. Secondly, you can attach business logic to these basically through an event subscription system. Every state change and everything in digital twins generates events that you can react to and that you can attach business logic for. And the third way is we are working on an integration with Azure Data Explorer for time series storage, so that you can basically run time series analytics on everything that you're doing, on all the data streams you have, and you can contextualize these time series queries with the graph queries. So directly from Data Explorer, you can actually run graph queries in Azure Digital Twins and contextualize the time series data with information from the graph. So these are just 3 ways how you can take advantage of the graph and derive insight and use it for operational decisions.
Sure. Is there some GitHub project or some documentation explaining or giving some examples of these?
Yes, there's definitely material on all of that, specifically to VSS, not because this is currently an initial evaluation, but yes, we can definitely share some content.
Okay, thank you.
Okay, thanks for your questions. Once again, if you can join us on Friday, we will have more time to go deeper into some of these questions. And hopefully, hopefully you can join us then. We are out of time for this session today.
Sure.
And thank you so much for joining. And of course, the key point for this activity is that we want to encourage all of you to join the normal everyday projects that are deal with this every week. So we have active projects on all of these topics, and you can join them to be part of that work. Thanks everyone for listening and being part of the workshop today. And talk to you soon. Bye-bye.
Thank you. Bye-bye.
Thanks, Gunnar. This was great.